Hello everyone, welcome to the Information and Network Security lecture series. This is lecture number 4. In the previous lecture we saw some of the monoalphabetic cipher techniques. Now in this particular session we will see some polyalphabetic cipher techniques. So as we know, in case of polyalphabetic cipher there is no one-to-one relationship between the plain text character and the cipher text character. Now here some of the examples are given, like Playfair cipher, Hill cipher, Vigenere cipher, Vernam cipher, and Onetime pad. We'll see these examples. So let us start with the Playfair cipher. So this, in order to do encryption decryption using the Playfair cipher, the very first step is we need to create a matrix, a 5 by 5 matrix. Okay, so this is a 5 by 5 matrix. In case if we are given a keyword, so here as you can see, the keyword in this case is prince. So this prince is the keyword. Okay, so we need to the very first step is to create a 5 by 5 matrix using this keyword prince. Okay, so how to create this? So we draw this matrix in this way. Okay, so I'll just write P R I. Now one more thing, because this matrix is 5 by 5, so there are
25
places of 25 boxes where we can put the alphabets, but in English there are 26 alphabets, so we need to skip one. So what we do is we generally write this I and J are written together. So you can see this I and J are written together, okay, to make this proper. So P R I N C and E. Okay, now after writing this P R I N C E, we now go through the alphabetical order and write all the missing alphabets which are not in the prince. So A, B, D, because C is already there, A, B, D, E, F, G, H, L, M, and so on up to Z. So the very first step is to make up this matrix, a 5 by 5 matrix. Okay, then second step is to divide the plain text into digrams. Okay, digrams means we divide the text message into pair of 2 alphabets. So suppose the plain text is attack is postponed. So what we do is we write this AT, okay, then TA, CK, okay, IS, POST, and so on. Now the last alphabet D cannot be paired because it remains alone, so we write a bogus alphabet X with this, so this becomes DX. Okay, so the second step is to divide the plain text into digrams. Okay. Then the third step consists of converting the plain text to the cipher text using some rules. So these are the rules, we must follow these rules. The first rule is that two plain text letters that fall in the same row of the matrix are each replaced by the letter to the right, with the first element of the row circularly following the last. What does it mean? Like suppose if you want to write this, like suppose I want to in my plain text, if I have something called as AD. Okay, I have to this is the suppose the plain text character. I want to get the cipher text for this. So A is here and D is here, both are lying in the same row. So first I have to get the code for A. So for code for A is the alphabet lying immediately after A on the right side, so this is B, and for D it is F. Okay, so for A we write B and for D we write F. Now suppose it may happen that we want to write the cipher text for suppose DF. Okay, DF. So for D, of course it is F, and for F it is E. Okay, we go in this circular way. Okay, so this is how, if the two alphabets are in the same row. Now the second rule is for the column. Okay, now what happens if they are in the same column? Okay, like suppose I want to encrypt this MU. Okay, MU. So when the two alphabets are lying in the same column, then the corresponding ciphertext alphabet for M is U immediately before M down the line, and U is Z. Okay, so for MU we have U, Z. For M we have U, and for U we have Z. Okay, let us take one more example. Suppose I want to write the code for FZ. Okay, so this is F and this is Z. I want to get the ciphertext alphabet for F and Z. Okay, so for F, immediate next alphabet is M, and for Z there is no alphabet, we can just go circularly, and so this C. So for FZ we have MC. So this is how the second rule says. Now the third rule, if the two alphabets are neither in the same row and the same column, then what happens? Suppose if we have in this example, so we want to write for AT, okay, A and T. Okay, we want to write the ciphertext for A and AT. Okay, so in this case, what we do is first we have to encrypt A. So we see the alphabet which is lying in the same row as A and the same column as T. So we write this D. Okay, so for A we have D, and for T we see the corresponding alphabet which lies in the same row as T and the same column as A. So this is Q. So this is how we write. Okay, if they are not in the same row and same column, this is the rule. Then finally it may happen that we may get two alphabets which are same. Suppose I want to encrypt different, D I F F E R E N T. This is the, suppose this is the word I want to encrypt. So this is the first pair. Now in this second pair, two F are coming together. Two alphabets, they are having the same thing. Okay. Now take care, in this ATTAC, when we make the pair, this two T they were together, but while making the pair they are separate, so no need to do anything here. But in this case, when we separate them, this F will come together, so we need to insert a bogus character here. Okay, so now we can do this. Okay, so we must take care about that. Okay. So you can check out, even in case if there is a repeated two alphabets coming together, we do that. Okay, now next we see the solution. Okay, so this is the different weapon. Okay, suppose we have different we have the plain text different weapons. So the first step is we do is we make pairs. As you can see, 2F, they are coming together, so Fx, we have written Fx, and so on. So for DI, this is BN, you can check it out. This is the key matrix, and this is the plain text in the cipher. This is how we do using the Playfair cipher. Okay, now next polyalphabetic cipher is the Hill cipher. Okay, now Hill cipher of course comes under the category of polyalphabetic cipher, and it is a block cipher. Okay, the second one is a block cipher. Why is called as block cipher? We take some blocks of data. We have something called a stream cipher, we have something called as block cipher. Stream cipher, it encrypts either 1 bit or 8 bits at a time, that is 1 byte. But a block cipher, it takes more than 8 bits together. Okay, it can take a 64-bit block also. So this is a block cipher. Now how do we do encryption using Hill cipher? Though, as we can see, the third point says that the plain text is arranged in the form of a matrix. Okay, of a matrix. Okay, which may be like n cross m matrix. Okay, it is a form of a n cross m. So we can have, like, suppose we have this plain text, we can arrange this plain text in form of a matrix, which can be n cross m, means n rows and m columns. Okay, it can be that way. Okay, then the second thing, the next thing what we do is we select a key matrix, which is of course a square matrix, m by m. Okay, and what we assume that whatever key matrix we are selecting, the corresponding that is the inverse of this k also exists. If inverse does not exist, then we cannot do this. So we select a square matrix k such that its inverse exists, that is k dash, that is k dash. Okay, next for encryption, what we do for encryption, we have the plain text. 1 minute, I'll just show this. So we have the plain text p. Okay, we post multiply this by the key matrix and we get the cipher text. Okay, this is how we get the cipher text, and this is sent to the receiver. What the receiver will do, receiver actually will post multiply this cipher text matrix with the inverse of this. Okay, and he or she recovers the plain text. Okay, so this is k inverse. Okay, so this is of course a simple mathematical part here. As we can see, for getting the cipher text, we multiply p with the key matrix, and to recover the plain text, we multiply the cipher text with the inverse of the key matrix. So this is simple. We can see this mathematically also. So see, we have c is equal to p cross k. Now if we multiply post multiply both the sides by inverse of k, the key matrix. So I multiply it here also, equal to p into k inverse. Okay, and as we know, this k into k inverse is I. So we have this c into k inverse into p into the identity matrix, because k into k inverse is identity, and p into identity is actually p. So this is what we get. Okay, so this is the mathematical proof that how we get this. So this is the Hill cipher. Okay, then next what we consider is the Vigenere cipher. Okay, now Vigenere cipher also comes under the category of polyalphabetic cipher. Okay, and it is the most, we can say, the most simplest polyalphabetic cipher technique. Okay, so what we have in this case, we consider the plain text to be consisting of a sequence of, let us say, m letters. Okay, like here the example is given, you also consider the example. So plain text is attack today. Let us attack today is the plain text message we want to encrypt. Okay, so it is a sequence of characters. Then the fourth point says the key consists of a sequence of n letters such that n is less than m. Okay, so here the key is smile. Okay, SMILE, smile is the our key letter. Okay, now how do we get the cipher text? Okay, so here the example and is given. Okay, and the cipher text also formed. So we have the plain text attack today and smile is the key. Okay, so how do we do this is, first we arrange the plain text character A T T A C K attack today one after the other, and then we arrange the key. Our key is smile, SMILE, but here we are still left to encrypt the plain text. So again we repeat the same key, SMILE, again S, and so on. If there had been 100 letters, 100 alphabets, we need to repeat this smile until we exhaust the plain text. Okay, now what we do, we apply the additive cipher. Okay, so plain text with key S we get S, plain text T with M we get F, plain text T with I we get B. Now how we get this? Now why it is, first of all let us see why it is called as polyalphabetic, because here we are having T, but here the cipher text here is F and here is B. We are not getting the same thing for the same plain text. And here again we can see T is of course coming as F, but it may not be so for each and every T. And here also we can see for A, here A is encrypted as S, and here A is as L, then here A as E, and so on. Okay, now how we get this is we can check this formula which we had used in Caesar cipher. Okay, so cipher text is equal to plain text alphabet plus K mod 26. We can apply this formula. Now how do we get this P? Okay, we need to write the number. Okay, we need to write the number of this plain text character, like A is given as 0, B as 1, and so on. Okay, so for A, whatever we get, we write P is actually 0 plus the K. So we get the corresponding number for S, whatever the number is, we put this number here and take the mod of 26. Okay, and then whatever number we are getting, we get the corresponding alphabet here. Okay, so you can try this. Okay, then next what we have is the next polyalphabetic cipher is the Vernam cipher. Okay, now Vernam cipher, in order to defend against any attack, it is required to select the key as long as the plain text. So this idea was given by Vernam, that why don't we have a key which is as long as the plain text. Okay, so of course this is a very good idea, so that if we have the messages as large as the key, then it will be impossible for to get the recover the key. Okay, now this actually technique works for binary data. And it is not for letters. Now this is what we have. Okay, the cipher text. So CI, okay, like PI XOR KI. So here XOR operation is used. Okay, so like suppose if we have 1 0 1 1 0 0. Okay, and suppose the key I am writing, this is the plain text, and suppose the key is 0 1 0 0 1 1. This is the key, suppose. So we do the XOR operation. Okay, so this is P0, this I, this is P1, P2, 3, 4, 5, and this is K0, K1, K2, K3. Therefore it is treated as K C suffix I, PI, KI. So that is the corresponding bit. Okay, now in with respect to the XOR operation, we know that 0 1 is 1, 0 1 is 1, 0 1 is 1, this is 1, this is 1, and this is 1. Okay, so XOR operation. Okay, how does this XOR operation works? For 0 0, if we have two inputs, so 0 0 is 0, 0 1 is 1, 1 0 is also 1, and 1 1 is 0. Okay, so this is what we get for the XOR operation, and of course it is reversible. Okay, this XOR operation is a reversible operation. Okay, like suppose if this is the plain text, This is the key and this is the ciphertext. So if we are XORing plain text with the key, we get the ciphertext, and if we XOR this ciphertext with key, we get the plain text back. Okay, so this is done in case of Vernam cipher. Okay, then the last one is the one-time pad. Okay, now what is the use of this one-time pad? This one-time pad, it utilizes the idea of Vernam cipher, but it has some more improvement as compared to the Vernam cipher. So it was proposed that we can use a random key. Okay, as long as the message, we can select a key which is of the same size as the message, but the difference here is the once the key is used, it must be discarded. So for every new message we have a new key. So every new message will have a new key. Okay, so every new message will require a new key having the same length as the plain text message. This is the difference as compared to the Vernam cipher. Now this technique is of course the one of the best possible cryptographic technique. Okay, it will become almost unbreakable by any means. Okay, but there are some problems which are associated with this scheme. This scheme is very nice, but it has its own problem. The first is the problem of generating random keys of such a big length. Okay, now it is not easy to generate a key such big length every time we need to send the message. Then second problem becomes the distribution of the key. How to send the key to other person? If we want to send 100 messages, we need to generate 100 keys and share the 100 keys. So that becomes a big problem. Okay, now although this one-time pad is the most secure technique, but it cannot be implemented practically. Okay. So that's all for this particular session. Thanks for watching.